Try that again with the sound on. Good morning. Looks like a lot of people are not here yet, so I'm going to go ahead and take attendance then. So if you're one of the few that are here, please send me your name and student number in the chat right now. Okay, send me your name and student number in the chat right now. Okay, nobody. Okay, there's one. Name and student number in the chat. Okay, let's go ahead then and finish up chapter 7. We just had a little bit. I'm going to do a quick review of the main points as we talk about the homework for this week. Okay, so remember, potentiometry is the Nernst equation where we measure potential, and that's going to tell me about concentration of some species. Really, it's activity, but we say concentration. So we use for this galvanic cells. And remember, we use 2 electrodes. There's the indicator, that's the one that responds to whatever I'm trying to measure, and then the reference electrode. So we just set them up, reference electrode, our indicator, and we put in a meter, measure potential. That tells us about concentration. Okay, and remember the general equation, really the only equation you have to remember for these is E cell is cathode minus the anode. Usually that's the indicator minus the reference, but sometimes those are switched. Okay, but really you don't have to remember these if you just remember cathode minus the anode. And then when you look at the cell, that will tell you which one's the cathode, which one's the anode. Okay, so there are 2 types of electrodes that we use in potentiometry. The first is metallic, and the second is membrane. So remember the metallic, we have these 4 kinds, the first kind, the second kind, the third, and then redox. So your homework, one of your homework questions was to say what kind of metallic electrodes each of these were. Okay, so all of these have a reference electrode, but we're not interested in that. We're always interested in the other half. Okay, so the first one is redox. Anytime you see 2 ions with no metal electrode that's the same ion, it's going to be redox. Okay, B, you have a metal responding to its own ion. That's always first. Okay, C, a lot of people miss this for some reason. Maybe they were looking at the reference instead of this part, but again, 2 ions and an inert electrode, so that's redox. D, this one's actually second. You have a metal responding to an anion from the salt. And then E, anytime you see EDTA and you've got 2 different metals and some other complexing agent, that will be third kind. Okay, and this one's unusual. Again, you're not going to see the third kind on a test or a quiz, so just kind of a hint there. The third kind will not be the answer. Okay, the other thing we had in the homework was to actually calculate the concentration of p-chromate. So this ion concentration, if we know that E cell is minus 0.386. Okay, so remember, our overall equation is always E cell is cathode minus the anode. So when I look at this, how do I know which is the cathode, which is the anode? And you do know just by looking at this. Remember, the anode is always on the left, and the cathode is always on the right. Okay, so just by looking at it. All right, so notice here the reference electrode's the cathode. This is not the usual way. So now we have to set up the equation. So we need to know what's that reduction for this silver chromate. So that's that reaction, and you can find E0 for that. And then we're just going to put it into the E cell, cathode minus the anode. So E cell is cathode, so that's going to be E of SCE, and then minus, and now we need a Nernst equation for this whole reaction. So notice that's minus 0.45 minus 0.0592 over N. Here N is 2 log of the chromate. Okay, products over reactants. All right, now put in the numbers you know. Okay, so they gave us E cell. We know this is always 0.244. That's a constant at 25 degrees C. And then we put in, we already know this from that half reaction. All right, now you just have to do the math. And so we move all of these over here, and then multiply by 2 divided by 0.059, and you should get 6.08. Notice 2 decimal places, okay? So, here 2 significant figures, these have 3. So remember, for a log number, the significance is behind the decimal. That 6 is not significant. Okay, so that one's 6.08. Most of you did that fine in your homework, so you either understand it or copied it from last year. We'll find out on the quiz. By the way, so next week we will have a quiz on chapters 6, 7, and 8. And there will be a calculation like this one on the quiz. And there will be a calculation like this on the final exam. So you have to know how to do this kind of question. Okay, that's the metal electrodes. So now we want to look at membrane. So remember, these are the ones that respond to an ion by developing this potential difference, because we have one concentration here and a different concentration here. And we get this potential at the membrane that's called the boundary potential. And remember, it's that boundary potential that's related to the concentration of what I want to measure. These electrodes are different than metallic. There is no redox reaction. Okay, it's just a concentration difference. And we talked in great detail about the glass membrane. And remember, this is the equation that governs that. For other membranes, they all have that same general equation. E cell is always a constant, minus 0.0592 over N, number of electrons, and then P ion. And remember, these do not have a redox. So we often call them ion selective electrodes because they respond to ions. So they're called ISEs. Okay, and for these, there are 4 types. We looked at the glass, and then we also looked at solid. We didn't talk about these other 2 kinds, but they're out there. Oh, there we go. All right. So we went over this last time, but I'll just mention again. This is just asking, okay, what do we graph for these ion selective electrodes? So remember, this is the general equation. Get my picture out of the way so you can see it. And so we talked about, and you did this in your homework. Okay, what do we put on the y-axis? That's always going to be the E cell that I measure. And here, always P ion. Okay, if you just put concentration, that's wrong. It has to be in the minus the log form, P ion form. Okay, so we're going to graph millivolts, which is the potential, versus P ion. And then it asked for the slope of the line. So it will be for 1 electron plus or minus 59 millivolts, and for 2 plus or minus 29.5. Okay, and then in your homework, we had one of these, but before we get to that, I skipped over this slide last time because we were running out of time. So when we're doing these calibrations, it's important that the ionic composition of your standard matches your sample. Okay, now why is that important? Why would that be important? Well, remember, part of that constant was that junction potential. And we said, oh, that's a constant, it doesn't change. But that's only true if your samples and your standards have the same ionic composition. And often they do not. So what we do in order to make sure they do is we have to add a whole bunch of inert electrolyte. And they add this thing, it's got a long name, total ionic strength adjusting buffer. And it has three things. It has sodium chloride, it has citrate, and it has acetate. Okay, and citrate looks like this. Citrate is a buffer, and then the acetate has this structure. Oh, sorry, the citrate has this structure and acetate has this structure. All right, so the reason we add this is because it makes the ionic strength and the pH of everything the same, of all your standards and of all your solutions. Now, almost all ISEs, you will use this TISAB. The one exception is if you're measuring pH. If you're measuring pH, you will not add it because it would change the pH of your standards. Okay? But if you're measuring calcium ion or fluoride or chloride or any other ion, you're going to probably add this. Okay, so your homework had this, and notice they talked about the pH and ionic strength were buffered. That's what they mean. They were adding this stuff so that everything has the same junction potential. Okay, so then you had to take this data and you had to make a plot, and your equation for your line should be close to this. If you're paying attention to significant figures, this is actually what it would be. And notice this is pretty close to what we said. You know, this slope should be 59 millivolts, and it's quite close to that. All right, then what you have to do is to take that equation and calculate the molarity for each of the samples. You need to do them one by one because mathematically, if you take an average and do it, it's not the same. In this case, you get the same answer, but really you should do it one by one. So you get this average, and then they're asking, is this in range? But the range is part per million. So remember, part per million is a milligram per liter. So I have to get moles changed to milligrams. And of course, we do that through molecular weight. And so these all this average comes up as 0.92 ppm, which is within the limit. Okay, now on the quiz, on the exam, I will not ask you to do this kind of question. It's a little bit too detailed, okay? But it's actually something you should know how to do. There's really nothing that hard here. Okay, so now to just wrap up this chapter, the applications for potentiometry. This is a very rapid, simple, inexpensive method. Detection limits, -5, -6 molar, so pretty good. But we have to be careful if there's things that are interfering. Then sometimes that can hurt your detection limit. So the common applications are things like, of course, determine pH. That's the big one. Also, there's a lot of agricultural chemistry. For instance, if you want to determine nitrate in soil, you can use this method. It's actually a liquid membrane. You can determine things in foods and drinks. Again, nitrates, fluoride, and bromide. Those would be solid state membranes. Calcium would be another liquid membrane. It's used in a lot of industry. You can see here for determining chloride, cyanide, fluoride. All of these are solid state electrodes. It's used in clinical chemistry. So you could determine sodium and potassium using a glass membrane and calcium using a liquid membrane. Okay, so common applications for potentiometry. One other thing it's used for is to do titrations. So you all have done titrations in the lab, and you know how difficult it can be to get that last half drop where the color just changes, and you're trying to determine, oh, did the color change or not change? So you could actually use a potentiometric electrode to determine the endpoint. Okay, so now instead of looking for a color, you actually are measuring potential. And then you could have a plot, and then you could do math on it, and then it would be very easy to determine the endpoint. This is a much more accurate way to do a titration. It's especially useful if you have a solution that's colored or turbid, that means cloudy. This is a great way. But it does take more time than the titrations you did in the lab, just with the liquid and the solution changing colors. One example, if you wanted to determine the concentration of aluminum, there is no electrode to determine aluminum. There's no ISE for aluminum, but there is one for fluoride. So you could actually take that solution of aluminum ions and add a solution of fluoride, and that will form aluminum fluoride. And then you use an electrode to measure the concentration of fluoride. So of course, at the beginning of the titration, there's no fluoride because it's all being used up to react with the aluminum. But as soon as the aluminum is gone, now the concentration of fluoride starts increasing, and then you can actually measure that endpoint. Okay, so a way to determine aluminum using potentiometry. Okay, so that is it for chapter 7 then. So we're going to go ahead and get out of that. We've already done all the homework for that. And we're now going to go over to coulometry. Okay, so coulometry is our last electrochemistry chapter. And there's actually two methods here, coulometry and electrogravimetry. This is probably our shortest chapter in the book, and we're going to go through it pretty quickly. There's going to be a few key points. You guys have done the electrogravimetry in the lab, if you're here and you've done the lab. Although actually it's not used a lot anymore. Coulometry is a more important method, but you haven't done that in the lab, so this one will be less familiar. Okay, so let's first kind of compare the potentiometry with this coulometry. So potentiometry that we just looked at, that's where we measure potential of a galvanic cell. Remember, those are spontaneous. And remember, we did this under conditions with no current flow or very, very small amounts of current. And there's no change in the concentration. Now, in contrast, the coulometry, these were usually going to control the potential and measure current, and these are electrolytic cells. So these are not spontaneous, so we need a power supply to make these happen. There's another kind of method called voltammetry, but we're not going to look at that, so you don't have to worry about that one. Okay, so chapter 7, potentiometry, those were galvanic, spontaneous cells. Chapter 8 is coulometry. These are electrolytic. Okay. All right, so what these are, both of these methods, it's where we're going to oxidize or reduce an analyte for enough time so that there's quantitative conversion to a new oxidation state. Okay, now, what does that mean? Quantitative conversion. Okay, we've talked about quantitative analysis. Remember, that's what is it? Okay, but here that doesn't make sense. What is it? Conversion. So this is a different meaning for this word. So a quantitative conversion means all of it. We're going to convert all of it. In fact, it's not possible to do all of it, but we can get most of it. And we'll talk about what we mean by quantitative conversion. Okay, so there's 3 methods actually. 2 of them are coulometry methods. Notice one of them we use a constant potential and one we use a constant current. And then there's electrogravimetry. Okay, so the coulometry methods, for these we measure charge, we measure Q. So we're measuring the amount of electricity that we need to convert the analyte to the new redox state. In electrogravimetry, you measure weight, physically weigh it. How much weight of the new species do you form? Okay. Both of these, there's a direct relationship between what you measure, between the charge or the weight, and the amount of analyte. These 3 methods do not need calibration curves. Okay, so if I say, oh, for coulometry and electrogravimetry, what should we put on our calibration curve? You say, nope, there is no calibration curve. Okay, we just talked about in potentiometry, what do you put on the calibration curve? Oh, E and P ion, but here, no calibration curves, okay, because we can directly measure the amount of substance. Okay, now these sound different than potentiometry, but we still use the Nernst equation. The Nernst equation rules all electrochemistry. And so we can actually use the Nernst equation to actually calculate what potential do I need to get, say, quantitative removal. So notice here I've got a solution of mercury 2, and I want to lower the concentration to 10 to the minus 6. So they want to know what potential do I need to do that. Okay. Well, this is a straight Nernst equation. Okay, so remember Nernst equation, E equals E0 minus 0.0592 over N log products. That's going to be 1 over concentration of mercury 2. All right, so they give us E0. And this concentration, we want it to be 10 to the minus 6. So we do the math and we get 0.67 volts. Now, if I just said, what is the cathode potential, and I said nothing else, that would be the answer. But notice this one says versus SCE, okay, which means in this case, SCE is the anode. So I have to take 0.67 minus the 0.24 for SCE. And now this is my final answer. Okay? All right, the second one, B, said, what if I want to lower the concentration to 10 to the minus 8? Well, exact same thing, except instead of minus 6, I use minus 8. And I get 0.61. And then I have to do versus SCE. And that's my answer for that. Okay, so this was one of the homework questions in your book that I've just done for you, but you need to know how to do this. There will also be a calculation like this on the quiz and on the final exam. A simple Nernst equation, nothing complicated here. So you just have to do a quick, easy Nernst equation. What potential do I need to lower the concentration to a certain amount? Okay, now we can also, if we're doing these depositions, okay, and in these methods, you're always going to have an ion that you're turning into a solid, in this case, a liquid. You're depositing it. So we can actually calculate, is it possible to deposit one ion and not another ion if you have a mixture? Okay? And again, we simply need the Nernst equation to do this. So in this case, I've got nickel and cadmium together in one solution. And I want to know, can I separate them? So can I deposit all of the nickel and get no cadmium? Or deposit all the cadmium and get no nickel? All right, so now we have to say, okay, how much do I have to get out before I'm going to say it's quantitative? Okay, remember I said quantitative means all of it. So we're going to say, okay, if I have only 1 part in 10,000 left, I'm going to say that is all of it. It's not all of it, but it's close enough. So notice the initial concentration is 0.1. So what do I need to get the final concentration for it to be considered quantitative? Well, if this is 0.1, then if my final concentration is what, 10 to the minus 5 molar, that's considered all of it. Okay, so here are the reduction potentials for nickel and copper. So the first thing we have to consider is, okay, if these two are together, which one is going to deposit first? Which one is easier to deposit? And of course it is nickel, the one with the higher reduction potential. So nickel will be the first one to start to deposit. So I need to calculate, okay, what E do I need to deposit all of the nickel? Okay, remember we said all of the nickel means the final concentration is 10 to the minus 5. Okay, so we use simple Nernst. And so it's going to be the E0 minus 0.0592 over N, which is 2 log of 1 over 1 times 10 to the minus 5. And I get minus 0.40 volts. Okay, so that's the potential I need to get all the nickel out. Now, we're trying to say, okay, can I get all of the nickel out with no cadmium? So the next question is, where will the cadmium begin to deposit? Well, we know the initial concentration of cadmium was 0.1. So I use a Nernst equation for that. And so we use its E0 and the initial concentration, and notice I get minus 0.43. Okay, so what does that tell me? That tells me if I can keep the cathode potential between minus 0.4 and minus 0.43, then in theory, according to the Nernst equation, in theory, I can do this separation. Okay, now it would be very nice if we could just stop there and say, okay, that's not too hard. But remember that the true potentials that we need are not just that simple equation. Yes, we have to look at cathode minus the anode, but we also have to look at the IR drop. And we have to look at these over potential things, okay? So it's not as simple as, oh, we just keep the cathode between minus 0.4 and minus 0.43. We also have to think about these other factors. And unfortunately, all of these change with time. And we're going to talk more about that. But first, let's review these over potential. We talked about that in chapter 6. So remember, what is an over potential? It's the extra energy we need to force an electrode reaction to go at the required rate. And these are always negative numbers. Even though often they give you a positive number, the number is always negative. And remember, there's two kinds. There's the concentration, which is when you don't have enough stuff coming to the electrode to react. And then there's kinetic, and that has to do with just slow electron transfer or other things going on. Okay, now both of these types, the concentration and kinetic, can occur at both the anode and the cathode. Okay, so our equation actually looks like this. Notice it's getting more complicated. So we still have cathode minus the anode and the IR drop, but now notice that we have the overpotential at the cathode from concentration and at the cathode from kinetic. And then the anode for concentration and the anode for kinetic. Okay, so now we've got, there's a lot of things here. Also, I should mention, notice here we're now saying E applied instead of before we were saying E cell. Okay, what's the difference? Well, in one sense they're the same, but often when it's a galvanic cell, we say E cell because that's the potential that we get out. Usually when it's electrolytic, we say E applied because remember, I have to put the energy in. And so we say E applied, so it's just clear that, oh, this is an electrolytic cell. This is the E that I have to put in to make this occur. Okay, so we need to look more closely at how do these things change with time and how do these affect the E of the reaction. So let's look at an actual example. So I'm going to deposit copper. And so my copper reduction reaction at the cathode is copper 2 going to copper. And E0 for that is 0.34 volts. And then the anode reaction is this. Now notice that the E0 applied would just be cathode minus the anode. So it'd be minus 0.89 volts at standard conditions. Okay, now this one is not standard. The initial copper is 0.022. The hydrogen and the oxygen are standard. All right, so then we would have to use the Nernst equation to calculate, okay, what is E applied? Just cathode minus the anode for this. So if you use the Nernst equation, it would be minus 0.94 volts. Okay, but now we have to, so we've got this part of the reaction. Okay, this part we can get from the Nernst equation. Okay, so we've calculated that part. Okay, all these others we actually have to measure somehow or look them up in handbooks. They have to be determined in the lab. Okay, so we now need to talk about each of these and how they might affect this reaction. So the first thing we should know is this cathode reaction, okay, the reduction of copper. Remember, that is a very reversible reaction. Remember, reversible means fast electron transfer, stable products and reactants. So this is a fast reaction, always fast. So this term is actually going to be 0. We don't have to worry about it because this is fast reaction. Also notice that this, the anodic concentration, notice what is being oxidized is water. Well, there's lots of water. There's always lots of water. So this term we can ignore. Okay, so it's getting a little bit better. There's less terms here. Now, as this reaction starts to go, that anode potential is actually not going to change very much in this case because notice that the copper concentration is pretty small compared to these. So we're not going to make a big change in hydrogen ion. So this is not going to change a lot during the reaction. Okay, so we've taken out those two terms and we've simplified this a little bit. All right, so now we actually want to get some numbers for these guys. All right, so initially, you can measure the current and the resistance of the reaction. So those are 1.5 and 0.5 ohms. In the very beginning, there is copper at the electrode. We haven't started yet. So in the beginning, this term is 0, the cathode concentration over potential, okay? Because in the beginning, there's copper at the electrode surface. And the overpotential for that oxygen reaction is 0.85 volts. Now, notice they said it's 0.85, but remember, I told you these are always negative. So this is really minus 0.85 volts. Okay, so now I can put in these numbers. So I times R minus this, and notice what I get, minus 2.54 volts. Okay, so that is very different than the Nernst equation, which said I need this. Okay, when I consider all of these other factors, the potential I need just to make this start is minus 2.54 volts. Okay, very negative reaction. Okay, now, unfortunately, as this electrolysis goes, as we start depositing copper on the electrode, everything in this reaction changes. You know, we did this in the beginning, but these all change as the reaction starts going. So notice the first thing that happens, we had copper at the electrode, and then all that copper gets reacted, reduced. Now there's no copper here. So this is where we get that concentration polarization. And that means now that the current is going to drop because there's no copper at the electrode to react. So our current's going to start dropping off very quickly, right after we start the reaction. Now that affects everything else. So of course, if the current gets smaller, the IR drop will be smaller. This anodic kinetic potential, that actually gets less negative, more positive. That's because if the current is smaller, then this is a smaller effect. This term that in the beginning we said that's 0, now it's not 0. That now becomes a more negative term. Okay, so as this reaction is occurring, we've got all these different things going on. Okay, so notice here's the cathode, and it is changing a little bit with time. Okay, here's that IR dropping off with time. Here's that anodic kinetic overpotential dropping off with time. And then notice the cathode plus this concentration cathode overpotential. That changes a lot with time. Okay, simply because there's no more copper at that electrode surface, so that current's dropping off. Okay, now, why is this a problem? Well, it's a problem because that potential of your cathode is changing with time. Okay, so notice this potential, it's supposed to be here for the reaction to occur, and now that potential of the cathode, it's getting more and more negative. Now, if you have copper in solution with other ions, say there's also lead and cadmium all mixed together, we're trying to deposit the copper. So as that cathode starts going more negative, once that potential gets here, lead also depositing. So we're getting copper and lead. And as it keeps getting more negative, now we get cadmium. So we got copper and lead and cadmium. And then when I get out here, now I'm also getting hydrogen gas coming off. Okay, so this is a big problem for my analysis. Now, I'm trying to just deposit copper, not all these other things. So one solution is if I could just keep changing the E applied to keep that cathode where I want it, then I could get a proper separation. But unfortunately, I can't really predict how the overpotential and the conductivity are going to change. So I can't just keep adjusting it. So we have a solution for this. and this is called the 3-electrode cell. And this is exactly what it sounds like. It is a cell that has 3 electrodes. So 2 of them we've talked about. There's going to be a reference electrode that always has the same potential. There's my working electrode. This is where I'm applying the potential to deposit copper. And now we're going to add a third one called a counter electrode. It's also called an auxiliary electrode. And this electrode's job is to actually get most of the current flow through it. Okay, so you have a cell that has these 3 electrodes all together. And what we're going to do is we're going to measure the potential between the working electrode and the reference electrode. Okay, remember, we want to keep that constant. But the problem is my working electrode keeps drifting off. And then that potential between those is not constant. So now this is where that other one comes in. We're going to have that counter electrode, and its job is to keep these 2 the same. So we want these 2 to be the same. And when this starts to drift off, here comes the counter, and it brings this back to get it where you want it. And then it starts drifting. And the counter brings it back. Drift, counter, brings it back. So we're keeping that potential between the working and the reference at whatever I need for my analysis. Okay, and you have to keep doing this because the concentration is changing throughout the whole reaction. So you can't just do it once, you do it over and over during the experiment. All right, so 3-electrode cell. Its job is to keep the working electrode at the desired voltage. All right, so that's what you need to remember about the 3-electrode cell. It keeps the working electrode at the desired voltage. Okay, so that no matter what's going on in solution, no matter how the overpotentials are changing, that voltage between the reference and the working always where you want it. And that means you don't get interferences co-depositing. Okay, so 3-electrode cell and the important point. So that's one of the main points for this chapter is why we need this 3-electrode cell. All right, let's talk now about the 2 methods. So the first one, electrogravimetry. So this is where we apply a potential to cause the soluble species to reduce or deposit. We've already looked at the deposition of copper, so we apply a potential so that these copper 2 ions in solution deposit as copper metal, usually on a platinum electrode. So what you do is you take your electrode, you make sure it's very clean and dry, and you weigh it in the beginning, and then you put it in the solution, you deposit copper on it, and then you weigh it at the end. This assumes that all of the copper is plated out. This word plate out means it's deposited. And it assumes that there's nothing else that's coming out with the copper, only the copper. So to do this, that metal that you deposit, it has to stick to the electrode very well, and it needs to form a nice smooth surface that you can wash off and weigh it without it falling off. So there's all kinds of different factors that you have to control. You have to control the amount of current and the temperature, the pH, complexing agents. And so there are handbooks that you can look up, what factors, what conditions do I need to deposit this metal that I want to do. Okay, almost always for these experiments, you will use vigorous, okay, that word means strong stirring. And you do this for 2 reasons. One, sometimes some gas bubbles will form on the electrode surface. And so the stirring helps knock off the gas so that the metal can deposit. The other thing is, remember we talked about mass transport? We said there's 3 ways for things to come to the electrode surface. And I said you should know those. Remember, they're convection, diffusion, migration. And you should know what each of those means. And remember, stirring is convection. So we stir so that we keep bringing new species to the electrode to react. Okay, if you don't stir, then it will take a long time for those ions to get up so that you get more stuff reacting. So we almost always stir with these. One thing you have to be careful about is often hydrogen gas will form during the electrolysis. And if the gas forms at the electrode, sometimes it can actually make that metal that you're depositing flake off, and then you can't weigh it and you'll get poor results. So sometimes what they do to help with this is they add nitrate. Nitrate is something that's very easy to reduce. So then the nitrate gets reduced instead of the water forming the hydrogen. Okay, so depolarizer for that. Okay, let's go ahead and take our break there. It's time. So we'll take our 5-minute break and then come back after the break and continue. Okay. So the applications for electrogravimetry are pretty much to determine metal ion concentrations. And these two tables are in your book. So notice that there are some methods where you just control the current and you don't need to control the potential. So you can use 2 electrodes and you just deposit one metal only. So notice in this table, all of these can be determined that way. That's the only thing you're determining. There's nothing else in solution. But notice they give you the conditions that you should use in order to form the best metal deposit. Okay, then there are a bunch of metals that you can actually determine from a mixture. So you can selectively determine only one. So this other table, for instance, I could just determine silver in the presence of copper and other heavy metals, or only copper in the presence of all of these. Okay. And again, there's handbooks you can look up to give you all the different conditions you need. So this is a good quantitative method. It's very accurate and precise. The only thing you're doing is weighing. Okay, you weigh that electrode in the beginning and you weigh it in the end. And you can use the Nernst equation to calculate, what potential do I need to go to a certain degree of completion. This method's also important for separating certain metals out of solutions. Sometimes there might be an ion that interferes with your experiment. You need to get it out. So sometimes you can remove it using electrogravimetry. Okay, so as I said, the conditions for lots and lots of different systems are in the literature. Almost always you're going to use this rapid stirring for convection. They'll tell you the best temperature, whether you need to do potential control and what potential you need and what kind of pH you need. There are also a lot of applications for electrodeposition that aren't analytical methods. We're not determining what is it, how much is there, but they use it to make things look nice or to fabricate different pieces of metal. They use it to recharge batteries. So lots of other uses practically for this method in real life. Okay, the instrument, you need a power supply. You're going to either have 2 or 3 electrodes. So if you need to control the potential, you'll have 3. If you don't, you'll have 2. So your electrodes are going to be an inert material, usually platinum. And the working electrode needs to have a very large surface area. You want lots of places for the metal to deposit on this electrode. You're going to need to stir it, sometimes heat it. And if you're doing electrogravimetry, you're going to need a balance to weigh your product. If you're doing coulometry, you use the same things, but then you need something to measure the charge to integrate the charge. So here's a common setup. Notice this one's only 2 electrodes. So we have our anode here, and then the cathodes are always very big surface areas, and then stirring. Okay, so that's electrogravimetry, and again, you did that in the lab. Okay, now the other method, coulometry. This one, we're going to actually use Faraday's law, which tells us the amount of charge or the amount of electricity, Q, is proportional to how much reacts. And so for this, we're going to measure how much Q I need to deposit my product. Now, coulometry is much more powerful than electrogravimetry. In electrogravimetry, your product has to be a solid that you can form a nice deposition and that you can weigh it. In coulometry, your product can be anything. It can be a solid, it could be a gas, it could be an ion, okay, because we're measuring charge, we're not measuring weight. So this has really good accuracy, and it's faster than electrogravimetry as well. So this is actually a better method, but it's harder, a little bit harder to do. The equipment's a little bit fancier, so in the lab you did electrogravimetry. Now, I'm not going to ask you a lot about coulometry. Really, there's kind of 2 things I want you to know about coulometry. I want you to know, what do we measure to tell us about concentration? And I told you we measure charge. And I want you to know that this method is more useful than electrogravimetry, okay? But I am going to give you a little bit of background about it. We'll go through it pretty fast, but again, I'm not going to ask you a lot about coulometry. Okay, so we said we're using Faraday's law. So we're counting charge, and to do that, we need to measure current. And the equations we use look like this. So the charge is equal to NF/Vm, where N is the number of electrons, F is a constant, Faraday's constant, V is volume, and M is the concentration in molarity. You can also do this with, instead of using Vm, use the weight, and to use molecular weight. And remember, Q is equal to I times T. So this is the equation they use. Often they'll use it in this form because they want to know how much weight was formed. For this method, again, you do not need any standards. You do not need a calibration curve because all of these are either constants or are things that we can measure directly. I put a couple calculations in here just so you can see. Again, I am not going to ask you to do any of these kinds of calculations. So we're going to deposit copper, and they tell us the current and the time, and then they want to know how many grams of copper and how many grams of oxygen did we deposit. Now, in electrogravimetry, we could only measure copper. We can't measure gas. Okay, so we're saying, oh, this is more useful. So we're using these 2 equations. Remember, Q is I times T, where T has to be in seconds. So we get 729.6 coulombs. And then we can calculate weight from that using this equation. And so notice we can get the weight of copper and the weight of oxygen, okay, simply by measuring current and time. Another example, this is one of your homework problems in the book, but again, you do not need to know how to do this. Now they're wanting to know how much time would we need to deposit 0.1 grams of thallium-3. Okay, so again, these are equations, and we're depositing thallium, which is 3 electrons. So I can calculate Q. I know N, I know F, I know the weight, I know the molecular weight. So this is my Q. And then remember, Q is equal to IT. So I can calculate time, but they ask for time in minutes. So I do a little bit of simple math, I get 2.95 minutes. Okay, so that's how, just a couple example calculations. So coulometry, there's 2 ways to do it. You can either do controlled potential and measure the charge for that, or you do constant current and then calculate Q by I times T. If you're doing constant current, you have to be sure that you're bringing enough stuff up so that it reacts. In both of these, again, we're assuming that all of this Q that we're measuring is actually oxidizing or reducing whatever I'm studying, not other things. Okay, so the controlled potential, this one will use a 3 electrode because we have to control the potential. Remember, we need to keep that working electrode at the value that I want. And why? Well, remember this same equation, all of these things are changing with time. Okay, so by controlling the potential, then we don't get other things reacting. Okay, remember, we're keeping the working electrode at the desired potential. All right, and then we use an electronic integrator to actually measure how much charge is there in the system. So lots of applications. We can count coulombs for anything. Doesn't have to be solids, things that have no solids products, gases, ions, as I already mentioned. There are over 50 inorganic elements that you can do with this method. We can determine the number of electrons for a redox reaction. So if you make a new compound and it can undergo oxidation or reduction, and you want to know how many electrons are transferred, this can do it. So notice we had this basic equation. So in this case, we would weigh out some sample and we measure Q. We can determine its molecular weight using other methods. We know F, so notice we could measure N and see how many electrons are transferred. You can generate things that are unstable, just using current to generate a small amount with very good control. Notice you can generate it in situ. That means during the process, you generate what you need to use. Okay, so those are the applications of the controlled potential coulometry. Okay, the other one is controlled current. These are actually titrations. So here we are using electricity to generate something that's going to react with something else. So we put a current through a cell until we get some indication that my reaction is complete. So we'll measure how much charge, and then we calculate the current and the time. And as I said, this has much wider applications. Well, I didn't say this. This has wider applications than constant potential coulometry. Okay, so both the coulometries are more useful than electrogravimetry. This kind of coulometry is more useful than the other one. Okay, so for this one, you're still going to have a current source and a timer. You'll have 2 electrodes and an electrolyte. And now we're going to do a titration, but we're not going to have that glass tube. There's no burette. Here we're going to use electricity to generate my titrant. So, for example, here is an example of a cell. And notice what we're determining is this guy right here, cyclohexene. And cyclohexene will react with Br2. Now, Br2 is not very stable. So what they do is in this solution, notice they have KBr. So they use a current to cause the Br to form Br2. Okay, and this Br2 then reacts with the cyclohexane. All right, now the question is, well, how do I know when I'm done? Okay, so here, these 2 electrodes, this is where we're generating the Br minus, and then that's gonna make the Br2 react with the cyclohexane. So How do I know when I'm finished though? I can see the reaction. Well, there's a few ways. So one way might to be visually. BR2 has a color. So know at the end point, okay, when this is all gone, then the BR2 starts to become excess. So maybe we could see it at the end point, but actually that is quite difficult to do. Okay, so two better ways to find the endpoint. One is to use ampeometric. So this is simply where you have a small current that you apply, and then you're going to measure for when there's a change. So you use a circuit to detect a change in the current. So going back to this guy, notice over here, these two electrodes are my detector. So what I do is I put a small current between those, and as long as this BR2 is forming and reacting, I'm not going to sense anything. But as soon as this BR2 becomes excess, now that BR2 will react, and it will actually go back to the bromide, and it will sense that, and it will tell you, oh, you're at your endpoint. So that's called ampeometric. Here's another reaction, same idea. I'm determining I- using mercury 1 ion. So I'm using current, so I've got some mercury. I use current to form the mercury 2, and that reacts with the I-. Now, at the end point, this mercury 1 starts becoming excess. So at the end point, now this concentration gets higher, and so there'll be a current increase because this is a conducting species. So that would measure that. So ampeometric, a very common way to do this detection. Another way, potentiometry. Okay, this one we can use an indicator electrode. So that is shown here in this diagram, and it looks kind of complicated, but notice I've got the same reactions up here. So here is my cathode, and here is my anode, and we're doing this same reaction. We're forming the mercury 1, and the mercury 1 is going to react with the iodine in the solution to make that reaction. Okay, now we keep these separated so that we don't get the mixing of these solutions. All right, so that's the titration. Now the endpoint, notice what I have here. Right here is my endpoint detector. And notice I've got a reference electrode, and then I have a pile of mercury. And here we have mercury detecting the mercury 1. So we have mercury detecting mercury 1. What kind of electrode is that? That's metallic potentiometry type 1, a metal detecting its own ion. So using potentiometry to detect that. Okay, so lots and lots of different things we can determine this way, doing these coulometric titrations. So here's a table just showing some. Here's what we're generating using current, and then all of these different substances listed here we can detect using this method. So as I said, very useful method, lots of things that we can determine. Okay, so these titrations are good when your titrant cannot be stored as a stable solution. So notice like, BR2, Cl2, we don't really want to store those. So it's good for forming that kind of thing. We use very small currents that we can measure very accurately. So even dilute titrations can be used. We don't need high concentrations, small amounts. In theory, we can count coulombs for any method where the current is measured by integrating. All right, so the good advantage, very accurate, because the only thing, a reagent is current. That's what we're measuring. So very precise method. And it's used for quantitative analysis to, as I've already said, generate unstable titrants and stable ones on a small quantity, and you need them very pure. We can use it to study redox reactions, And we could use it to actually measure F. You say, well, we know what F is, but if you ever wanted to measure it, you could use this method. And notice you could measure it to 7 significant figures. Okay, now, I'm always yelling at you about significant figures. And almost never can you get 7 significant figures. But you can with this method because you can measure small amounts of current very, very accurately. Okay, so that's chapter 8. As I promised, quite short. So you need to make sure that you look at all of the homework problems in chapter 8. And you need to know how to answer 1 to 6 and number 8. Okay, number 7 and number 9, you do not need to know how to do those. 9 is a coulometry question that I showed you. 7 is like the one we did earlier in the class with the IR drop and the overpotential. And I'm not going to ask you to do anything that complicated for the test or for the quiz. Okay, so we have now finished electrochemistry. So next week, we're going to have our 3rd quiz. And this will be on chapters 6, 7, and 8. Okay, so the 3 electrochemistry chapters. And again, we will have this quiz on Thursday afternoon, not Friday morning, Thursday afternoon. The quiz will start at 1:30 p.m. on RAIN, and it will be about, I'll give you 45 minutes to do it. You should be signed in and ready by 1:25 so that you don't miss any of the quiz time. I suggest you use your computer. We're not going to use the monitoring system for this quiz. But remember, for your final exam, you have to have your computer and your phone to monitor. And so you need to be familiar with using RAIN on your computer and how to get the pictures into that. So it's up to you, but I suggest your computer on RAIN. Okay, there will be 2 calculations on this quiz. One of them will be like number 4. From chapter 7. So that was the one I talked about at the beginning of today's class. The other one will be like number 8 from chapter 8. That's the one that I did today in class as well. So both of these I have talked about today. So make sure you understand how to do those calculations. There will be calculations that are just like both of those. Okay, so this quiz will again have multiple choice unless it tells you otherwise. If it says choose 2 or choose all of them, then do that, but otherwise 1 answer. This quiz has some true, false. So remember, true, check mark, false, X. There's some matching. So remember the matching, you need to use this number letter system. There'll be some short answers and then the 2 calculations. Okay, are there any questions about that, about the quiz or about chapter 8? Okay, for those that are watching by video, you need to send me an email telling me when is the next quiz. I want the date and the time. Do not forget to give me your name and student number. If you're watching live, you should have given me your name already in the chat. Okay, but if you're watching by video, send me an email with your name, student number, the date of the next quiz, and the time. Okay, so we actually have a few minutes left, quite a bit of time left. So we're actually going to go ahead and start our next chapter. Oh, question. Let me see if that's question or attendance. Oh, looks like attendance. Okay. All right, so we're going to go ahead and start chapter 9 now. We won't get too far in it, but just to kind of get a start on it. And you won't have homework today. Your homework will be to study for the quiz that is next week. Okay. Okay, so our last 3 chapters are this thing called chromatography. So chapter 9 is kind of the introduction. And so there are many different separations where you have to first get your analyte separated from the matrix and then analyze it. That's what these next 3 chapters are going to be looking at. So chapter 9, 10, and 11. So chapter 9 is the general kind of introduction chapter. And then 10 will be looking at what's called gas chromatography, and 11 is liquid chromatography. There is another kind of separation called electrophoresis. It's becoming a lot more popular, especially for biomolecules, but we won't talk about it in this class. Okay, so chromatography comes from 2 Greek words. Chroma means color and graphene means to write. So this word means color writing. And it originally came from a Russian botanist. Okay, botanists study plants. And he was trying to separate the pigments in the plant. So he actually took this column and he packed it with calcium carbonate. And then he put a solution through it and he got these colored bands. So they called it color writing. So this is actually an extremely powerful separation method. There have been at least 12 Nobel Prizes for this method. Now, notice most of them were a long time ago, 50 years ago, but this method continues to grow, continues to develop, so it is still a very important method today. Okay, so generally, these chromatographic methods kind of have 2 parts. The first part is what we call a stationary phase. So this word stationary means it doesn't move, it stays in one place. And usually the stationary phase is either a solid or it's a liquid that they've stuck on to a solid. So the stationary phase doesn't move. And then the other part is what's called the mobile phase. And the mobile phase can be either a gas or a liquid. So the mobile phase moves through the stationary phase and comes in contact with that. So we choose these 2 phases so that my analyte will go back and forth between the 2 different phases. We want it to spend some time in the stationary phase and some time in the mobile phase. Okay, so it will distribute itself between those 2 phases. All right, so the mobile phase job, it is to carry, to transport, to move the sample through the stationary phase. And if you have a compound that really likes the mobile phase, then it will stay in the mobile phase mostly, and it will move quickly through the system. If you have compounds that like the stationary phase more, they will tend to move slower through the system because they spend more time in the stationary. And we say that they're retained. That word retained means they're held back. Okay, they're held back. So as your sample's moving down the column, it's separated into what we call zones or bands. And actually what happens is all the molecules that have the same chemistry, they will come out together. And those that have different chemistry, they come out at different times. Okay, so let me give you kind of an example of this. Do you guys recognize this? This is in Tianjin. Okay, this is Binjiangdao, okay? And what do you do at Binjiangdao? Well, you go shopping. Now, this was taken before COVID, so a lot of people here, no masks. So Binjiangdao, you can go there to go shopping. Now, what do you go shopping for at Binjiangdao? Well, clothes, shoes. There's supposed to be a lot of good food there. Okay, maybe a few other things, but those are the main things. Now, let's imagine that down the middle of Binjiangdao, we're going to put one of these moving walkways. Okay, and we're going to make it just go one direction, and we're going to take off these edges. Okay, we're going to take off the barriers. So we get rid of these. It's just one big walkway so that you can get on and off as much as you want. Now, if it was possible for the whole class to get together, and we all met at Binjiangdao, and we all started at the top. Okay, so we get on that walkway, and we start going down it. Now, there are some people like me, I'm not really interested in shopping. So I'm just going to stay on that walkway, and I will get to the end pretty quickly, as fast as you can. So I just stay on the moving walkway. There are other people that love to shop. So they're going to be on the walkway, and then, oh, a store, they get off, and then they'll come back, and then, oh, a store, and they get off and come back, off and come back. So it's going to take them a long time to get out at the end. Most people are in the middle. You know, maybe somebody's really hungry. There's a group of boys maybe that are hungry, right? So you get on, oh, food, get off, get on, oh, food. Well, okay, and maybe they'll all come out. So you can see that people will kind of maybe get separated into groups according to how much they want to go shopping and what they want to shop for. So this is the same idea for chromatography. These molecules are moving down the column and going back and forth between the mobile phase and the stationary phase, and they will get separated according to how much they like the stationary phase compared to how much they like the mobile phase. Okay, so when we talk about chromatography, there's two ways that we can classify it. The first is the physical way that the mobile phase and the stationary phase come together. So we talk about planar chromatography. This is where the stationary phase is a plane, and then the mobile phase moves up by gravity or what we call capillary action. This is an example of that. This particular method is something called TLC. So you would put your stationary phase here at the bottom, and you put it in a liquid that gets carried up, and notice you can see this compound's been separated. Okay. The other type is the one that we are interested in. This is column chromatography. So here we put my stationary phase in a column, and then things move by either pressure or gravity. So notice here, I put it here at the beginning, then I wash mobile phase through, and then things get separated. This one shows it by gravity. We will be interested for a method of actually using pressure to push this through. And these two ways are closely related, but again, our focus in this class for an instrumental method is column chromatography. Okay, the other way we can talk about chromatography is based on the type of mobile phase and stationary phase and the type of equilibrium. So if the mobile phase is a gas, we call that gas chromatography. If the mobile phase is a liquid, we call that liquid chromatography. Gas chromatography has to always be a column because otherwise the gas would escape. Liquid can be either column or planar. Okay, and we will be talking about both gas and liquid. Gas and liquid can be further divided into different types depending on the type of equilibrium that this table shows you about. And so when we get into chapter 10 and 11, we'll actually be looking at these different kinds of equilibriums and these different kinds of GC, gas chromatography, and LC, liquid chromatography. Okay, so we've already kind of looked at the general process. We said the first thing we do is we put our sample here at the beginning. That's called injection. And then we're running mobile phase through this column, and these things go down, and they're going to be going back and forth between the mobile phase and the stationary phase according to their chemistry. And as they go down the column, they're going to get separated. And then here we see A's coming out faster, and so we could actually measure it, detect it when it comes out. We get a peak, and then later B comes out, and we get another peak. So this plot of the detector signal versus time is called a chromatogram. Okay, a chromatogram. Okay, so some of these concepts in words. This process of flushing things through the column is called elution chromatography. Okay, and the mobile phase is sometimes called the eluent. So as this sample is going down that column, again, it's distributing itself back and forth between the stationary phase and the mobile phase based on its attraction for each. Okay, and this is called partitioning. Okay, partitioning. That's this going back and forth between the mobile phase and the stationary phase. We can also talk about the migration rate. This is how fast something moves down the column. And the more time it spends in the mobile phase, the faster it gets through the column. Okay, now you might be thinking, oh, finally there's a word that I know. You know, there have been lots of new words already. I know migration. Unfortunately, migration in chromatography is not the same as electrochemistry. Okay, remember in electrochemistry, migration is when I have a charged electrode, say a plus electrode, and then minus ions being attracted. Okay, so electrochemistry, migration is attraction of ions. In chromatography, migration just means moving down the column. Okay, so as these things are moving down the column, the one that's more strongly retained, remember, held back, that one comes out last. As I already said, that plot of the detector response versus elution time, that's called a chromatogram. And we can use the position of that peak, the time that it takes to come out, that gives us a little bit of qualitative information. Remember, what is it? The area under the peak, that gives me quantitative, how much is there information. All right, so going back to this picture, we've got A and B partitioning between mobile phase and stationary phase, going back and forth and coming out. So a couple of questions for you. As we look at these, which interacts more with the stationary phase, A or B? Well, interact more with the stationary phase, it comes out later, so that would be B. Which one is more strongly retained? Okay, remember, retained, held back, so that's going to be B. Which one has the faster migration rate? Okay, which one moves through faster? Well, that's A. And which one elutes first? Okay, elutes means comes out first. Okay, that's going to be A. Okay, so as we think of these guys going down the column and coming out, we can talk about something called migration rate, how fast it moves down the column. Now, notice here, this is signal versus time. This one is concentration versus distance traveled. Okay, so notice that A comes out sooner, so A always travels farther. Okay, so that's why these are flipped in these two pictures. So B is the more strongly retained by the stationary phase, so we know that it migrates slower. And the longer these guys are on the column, the more separated they get. You can see that here. Here, not separated, better. The longer they're there, the more separated they get. Unfortunately, the longer they're on the column, these peaks actually get broader and broader and more dilute. So these peaks getting broader is what we call zone broadening. Okay? Zone broadening. All right, so zone broadening is proportional to elution time. Okay? When they come out fast, the peaks will be narrow. When they come out slower, the peaks will be broader. And you can see that here. So, if we stop them right here, then we have pretty narrow peaks, but the separation isn't so good. But the longer they're there, the broader their peaks will get. Okay, and one other term we need to talk about is this idea of resolution. Okay? Resolution is how well separated the peaks are. So if you look at this top picture A, you can clearly see that these two peaks are not well separated. They're together. So we would say the resolution is poor. Now, resolution depends on two things. It depends on how far apart these two peaks are, and it depends on broadening, how broad these peaks are. And we can adjust the resolution by changing the experimental conditions. So we could try to adjust the migration rates. So we try to make this peak come out faster and this peak come out slower so that we get a better resolution. Another thing we could do is to adjust the zone broadening and try to make these peaks narrower. And then we could also get a better resolution. Okay, and we will talk much more about how we do these things as we go. But for right now, I'm just trying to introduce you to some of the vocabulary that we're going to need. Okay, so we actually will stop here. But so far, I have talked about stationary phase and the mobile phase, this process of elution, the process of flushing things through a column by adding mobile phase. Elute means to come out. Okay, retain, to hold back. The migration rate, how fast something moves down a column. The zone broadening is how wide those peaks are. And then the resolution, how well they are separated. Okay, so for next time, we will pick up right here and we will start developing some of the equations for chromatography, and we'll look at how we use those and what they mean. Okay, but remember, next Thursday, we have our third quiz on chapter 6, 7, and 8. Later today, I will post the homework answers for chapter 7 and 8 that you don't already have. And then I will eventually post the video. That always takes a few hours to get it compiled and compressed and uploaded, okay? Just so you know, the video always uploads much faster to Baidu and Dropbox. So if you get tired of waiting for it in WeChat, you can always get it there. Okay, we will stop there for today. So have a good week, and don't forget, quiz next Thursday.